Hello, we are back, okay, to continue our lecture from last time, okay. Last time we finishing our topic on, this one, the heat equation, the two-dimensional heat equation, and we will recall this partial differential equation again, okay, and you know that is the change of the heat, okay, over times, okay, is equal to a conversion unit, okay, multiplied by the summation of the change of the heat over the domain of the area, okay, that the heat that spread, okay, or transfer within a boundary condition, okay. But we really consider this equation physically, okay. When you reach some steady state, okay. Okay, what is steady state in engineering or even in physics mean that is that when system reaching for something that's stable, okay, we will assume that there'll be no change, okay, of the interested response over time, okay, which is mean that the rate of change of the thing that you are interested over time becomes zeros, okay. So when you consider this two-dimensional heat equation down here, okay, when rate of change over time is zero, okay, that, and you know alpha square is some positive value, okay, or constant value. So this lead to this relationship, okay, that once the rate of change over time is zero, it means that the acceleration, okay, of the response that you are interested over the domain, each domain, okay, for uh, each domain interested within the area. In this two dimension, we represent the domain as the coordinate of x, y, okay, within the boundary that you are interested becomes zero also. And this relationship and this equation is well known as what we call the Laplace equation. Okay, so in these clips, okay, we'll be interested to study how do we solve the general equation, a non-trivial solution for u of x, y, okay, that satisfy a certain boundary condition, okay, and that lead to this relationship of Laplace equation. Okay, we'll start by applying the what we call the separation function technique, or in other words, we when you read some of the textbook, we refer this technique as what we call Fourier method, okay, which is the multiplication of a separable function that rely on each domain. In this case, we're looking for a function of u of xy, okay. Therefore, u of xy can be represented as a separate function multiplied to each other corresponding to each domain, okay. And the same way that once u of xy is using this separable function technique representation, okay, with this relationship of Laplace equation, you can end up having this relationship because this is the second order, okay, that's the relation, this means the second order, okay, of this u function over x, and yeah, the second order of u function over y, okay. Therefore, when you apply this separable function, this becomes the second order just for the x, and y become the constant value, and and the same as the second term, that they become the second order of y, of capital Y function, okay, and capital X function corresponding to the domain x become a constant, okay. Then, okay, we apply a pretty similar technique that, okay, you can see that once this is zero, okay, you can move one of them to on the other side, okay, and then you can that lead you to this relationship, right? You remember that this time this, okay, equal to minus of this time this, because when you move this right hand side to left hand side, lead back to this equation, okay. So since these two are equal to each other, we're gonna assume it as a what we call the k square. Okay, the k square is a constant value. Okay, that can be positive or negative. Okay, remember that k square doesn't have to be positive all the time. Okay, we only interested that the k square. I think that we use this different notation when we apply for the heat equation. We assume as a lambda. Okay, but in this case we're gonna put it in as a k square. Okay, why k square? Because you have to remember that this is a second order equation. Okay, well, so when the second order equation, you with this relationship, you can lead to these two corresponding ordinary differential equation. Okay, this one, once this is equal to k square, you can get these two equation by use the first left hand side here equal to k square and the right hand side equal to k square, and then you end up having these two ordinary differential equation, and these two ordinary differential equation lead you to this general solution here. Okay, this general solution. Okay, why here? Because if we assume that if k square, okay, is some positive value. Okay, so this gonna be uh, the auxiliary equation here will be s square minus k square equal to 0. Therefore s will be equal to, plus or minus k. Okay, plus or minus k. And when you have a plus or minus k, since k square, okay, is some positive value. Okay, so k and minus k have to be the real root. Okay, this lead you to this general equation. Okay, and the same here. Okay, since k square is a positive value. Okay, uh, you end up, okay, having getting this as a complex conjugate. Okay, when you solving for the root of equation here, and but the real part is 0 here. That this lead to the general solution here, that no they have no content related to the exponent function that multiplies this, because the exponent function is e to the they have a 0 power that have therefore is equal to 1 times this function. Okay, that's all refer to the old knowledge of the ordinary differential equation. But you might interest that suppose k square is minus. Actually, if k square is minus, it's going to be reversed between these two functions. X become y become x, which is lead you to the same same formula, same form of u of xy. Okay. So again, let me tell you that in this case, we're going to assume this as a k square, which is the positive value, and can be either positive or negative value. Okay, if the positive value, if k square is a positive value, this is a general solution. If k square is negative value, it's going to reverse the form. Okay, k become x become y become x. That have a same general form of solution also. Okay, so therefore it's easy to see that now the general formulation of u of xy is this. The next step is that we need to find the coefficient of c sub 1, c sub 2, c sub 3, and c sub 4. And c sub 1, c sub 2, c sub 3, c sub 4, okay, can be found, okay, using what we call the boundary condition, okay, which will be different case by case, depend on the type of nature, the formula of what we the condition that function that related to the boundary condition. Okay, we're gonna show you graphically, okay, the representation of the uh, Laplace equation down here by look at this graph. Okay, uh, suppose that you have a rectangular space, okay, that have a domain, range of domain that x is between 0 to L sub x, okay, L sub x, okay, and y start from 0 to L sub y, okay. But in this case, okay, we're gonna assume L sub x approaching the infinities, okay. But in general, okay, it can be any finite or infinite value, okay. u of xy is a type of function that related to the domain within x and y. Okay, and the boundary condition is that, okay, at x is equal to 0, okay, you get for all y, okay, from 0 to y you have u at 0 and for all y. And then in this one, at y is equal to 0, you have u at x at y is equal to 0. And the same when you reach the boundary, okay, on the upper limit of both x and y, you have u of L sub x, okay, which is the limit of x, okay, here, okay, the maximum value of the possible x with all y. And this in this side also you have a u, okay, for all x, okay, from 0 to L sub x, okay, at y equal to L sub y, okay. In the real application, you might interest that if you think that the two famous application of this type of problem is one in the certainly the heat transfer equation, the heat equation that we extension from the steady state of the heat equation. Okay, the second one is if you study electrical engineering, this is a classical problem of the when you study the um, dispersion of the electromagnetic field, okay, within a finite space, okay. But we're not gonna go to all of this. That's in the more direct application class, okay. But in this class, we'll be more concentrated on uh, mathematical point of view, which is the general solution here, okay. In this case, okay, we're gonna start here that suppose we all have all zero boundary condition at u x 0, okay, and u at for all x at L sub y, okay, which is this one and these two side, okay, 0. Oh no, sorry. U of 0 or y here is 100, all 100. It's a constant value. And u of x0, okay, or the other three, okay, the remaining three side of the boundary condition are all 0, okay. Yeah. Actually, you might interest that if all sides are all 0, okay, if all sides are all zeros, okay, there's one non-trivial solution that the trivial solution that you can find is all c constant value are all 0, which is not necessarily that you want to find uh, the solution for this problem anyway, because we are looking for is that what we call the non-trivial solution. What is the structure of c sub 1, c sub 2, c sub 3, and c sub 4, okay, which again, okay, this problem can be working again and again and again depend on the type of boundary condition gonna look like. So this is an example that I want to show you that. So in this case, suppose that L sub x is approaching infinity, which means that on the x side start from 0 can be reaching the positive sign of infinities, okay, down here. But L sub y has some finite value, okay, has some finite, it's not reaching a very large infinity value, okay. Okay, we're going to see how this condition affect what you're looking for, c sub 1, c sub 2, c sub 3, and c sub 4, okay. Okay, let's look at the first condition. You know that that this u of x is 0, okay, at y is equal to 0 is 0, okay. And if you substitute y 0 here, okay, y is 0 here, you know the sine term becomes 0. Sine 0 is 0. And cos 0 is 1. Therefore, you have c sub 3 remaining in the for the y function as a constant. But for the x function, okay, x is always the remaining variable. Therefore, okay, this is how the results gonna look like. Okay, the second, the y function becomes the constant c sub 3. And you know that this is 0 to 0. But for all x doesn't have to be start from 0 to alphabet, okay. Okay, therefore the only condition that will hold, okay, for all x, okay, is can be concluded in this case for this equation going to be satisfied, okay, only c sub 3 is always equal to 0. Okay, so now you know that c sub 3 is 0. Okay, And with this, you know that the second term, this is the remaining second term. Okay, the first condition lead you to have a conclusion that c sub 3 is 0. So the second, the y function have this only remaining term. Remember the phi function here? Okay, since c sub 3 is 0, this is the remaining term. Okay, so the second condition is u, okay, when you go to alphabet, okay, when x reaching the maximum value, alphabet, and y is equal to, but remember that alphabet is infinities down here, okay, reaching infinity down here. Okay, so you get this equation. Okay, you know, for all y, okay, but you know that when you substitute x at alphabet, okay, down here you get this. But you know that since alphabet we see in this condition is reaching the infinities. Okay, so look at the second term. Okay, and now you know that k here is a positive value. Okay, can be either positive or negative value. Okay, but in this case, okay, we're gonna assume that k is a positive value. Okay, you can see now that when alphabet, okay, reaching the infinity, this term become vanish because it's become e to the minus k times infinities, okay, which is a 1 over e to the k L of e times infinity. When you take a limit of alphabet equal to infinity by L'Hopital rule, okay, you get to see that this term is vanished. So when this term is vanished, okay, this is the remaining term. The remaining term, okay, if alphabet has a very large value, okay, it's gonna be vanished. Okay, this condition not gonna be satisfied for all y unless c sub 1 is 0. Okay, so this condition lead you to have a conclusion that c sub 1 must be 0 here. Okay, so when c sub 1 is 0, therefore, okay, the remaining term here of u of xy is, you can look at here that when c sub 1 is 0, okay, and you have c sub 4 is 0, so the remaining term will become here. Okay, this is the remaining term. You can see that c star over here, you can see that is a multiplication of c sub 2 times c sub 3, because c sub 1 is 0, c sub 4 is 0, so u of xy have only these two terms multiplied to each other, the c sub 2 e to the minus k times x times c sub 3 cos of k times y. Okay, so when c sub 2 and c sub 3 multiply to each other, is a constant, we become the new constant we call c superscript star, okay, c sub star, okay, times e to the minus k times x sine k sub y. Okay, so we can use the third condition now. Okay, at u at x at ly, okay, u for all x, okay, at the upper limit of y. Okay, so you can see that, okay, this is c star e minus k times x sine k ly. This must be 0. And this must be 0 lead you to a nature of the k value here. You can see that k value over here need to be equal to n times phi divided by I times 1. Because the only way that for all x that this condition going to be satisfied is that the term sine of k times ly need to be equal to 0. Because we cannot control e to the minus k times x for all x to be 0. Okay, we cannot control the c star down here, but we can control here. Okay, this leads you this condition of k. And n can start from 1, 2, 3, actually 0 also. But 0 is a quite a trivial case, okay? But this one, n equal 1, 2, 3 are up to infinities. And this leads you to this general form of the results of u. And we have one parameter at n value. And this c star have to also depend on case by case, depend on the k. Look like that k depend on n, therefore c star depend on n. Okay, and we substitute the k value according to this third boundary condition, and now you get the parametric u function of xy that depend on n down here. Okay, depend on, okay, Remember that we add n here because remember from the heat equation that u of xy at first did not rely on n, but since the k value, okay, down here to satisfy the boundary condition rely on the new parameter called n. Therefore, un of xy have several type of feasible function depend on the n value here. In this, that's become the parametric form of u of xy. And we can apply this for the fourth boundary condition then. So for each n, okay, we know that u, okay, for all n, okay, at 0 y have to be constant value 0. This is so this one we substitute from here, okay. You get this, okay, cn, okay, and you know that when x is equal to 0, okay, this term become 1. Okay, so this one is, and also this one rely on n, okay, for each possible n. And by superposition principle that we apply for the heat equation, therefore, in general, u as 0 and y can be, okay, the combination, okay, the summation of all n, okay, of c star n, the constant value, times sine of this ky, okay, with this condition, have to be equal to 100. Okay, so the key problem is here that what is C star n gonna look like, okay, for this boundary condition, okay, and you know that in general, okay, u of xy have to be equal to summation n for all n of C star n here, but we have this boundary condition down here, C star n sine n times pi y divided by L sub y equal to 0, 100, okay, so you can see that with this boundary condition, okay, if you choose it step by step, okay, you'll be able to eliminate, okay, especially the zero constant here, and simplify the function, okay, step by step right here to get this resulting function, okay, as a solution. But still we still need to find what is c stars of n, okay, gonna look like, okay. Now, okay, we applying a similar technique that we used before, okay, that when you apply the heat equation, okay, you can see this is the left hand side for this boundary condition, and this is the right hand side, okay. If we multiply both sides, okay, you remember that this is the original one. We apply, this is for summation n, this is a general term. If we multiply both side by sine of m pi y divided by L sub y, on both sides, and we integral on both sides from 0 to L sub y, okay, dy. Okay, therefore from this equation you multiply both sides by sine of m pi y divided by L sub y, both sides, okay, this 100, and we integrate, okay, over the range of 0 to L sub y, okay, dy, okay, here, okay. You end up having this, okay, okay, on the left hand side you have size sum, okay. Well, you remember that n is you contain in summation, but m is a can also have the same running number of start from 1 to infinity also, okay. And when you apply this, okay, on the left hand side the size sum, you can use this trigonometry, okay, properties, okay, to separate the summation, the multiplication term to summation term. Okay, so when you apply this to this, okay, you get this result, okay. And for the left hand side, okay, once you multiply 0 to y down here, okay, you end up, okay, let's try to look at it. You get sine, okay, you get the the derivative of sine, that you get the sine is a cos. The derivative of cos, you get minus sine, okay, and that's how this is a basic calculus, okay. You can evaluate this, okay, when you substitute y by L sub y. If you want to substitute y by L sub y, you get 0 here, okay, since this is a sine m pi, okay, sine m times pi, when m start from 1 to it's always 0. But on the left hand, but when you multiply here at 0, okay, multiply here 0, okay, you get, but in this case, okay, there's only one case that happened, okay, before we evaluate this term, it's gonna, we take a look at the left hand side first, okay. For the left hand side here, okay, you substitute here, okay, equal to, if you really consider this cos and this cos minus integral, okay, and for all n, and with n is not equal to m, because with n is not equal to m, okay, there's gonna, on both term is gonna be a non-zero angle for the cos function. And when you zero angle mean that the multiplication of the domain y here is you have non-zero constant multiply. With this function, okay, when you integrate within this range, okay, it's always 0. Okay, that's not hard to evaluate. Okay, this is your direct substitution from the calculus. Okay, but only one case that is going to be non-zero is when n is equal to m. Because when n is equal to m, okay, this cos function become 1. Okay, the constant value 1. But the second term is still maintain the cos function, which if we integrate between 0 and y, the second term is 0. When n is equal to m, the second term is, but the first term, you have a constant value of pi times y divided by ly. Okay? And you know that when you evaluate this, the second term is 0. Okay, the first term is that when n is equal to m, okay, you have one value, okay, no, this is the whole angle here down here, okay, and you know that this become the 1, okay, the value of 1. So this is the half of the first term is 1, the second term is a non-zero. Since n is equal to m, this become 2 times n. And the integral of the second term is 0, okay? But the first term is you have L sub y minus 0, okay? Then you have L sub y divided by 2, okay? So this is the left hand side. The left hand side, the only term that remaining is that when n is equal to m, because the remaining term is always 0 when n is not equal to m. Therefore, the summation down here, this is a reduction of the left hand side. It's only c star as n is equal to m is m, okay, times this term, okay, when n is equal to m is L sub y divided by 2, okay. For the right hand side, okay, certainly the 100 value is here, okay. And again, okay, if you want to find the integral between 0 to L sub y sine m times pi y divided by L sub y, you just this is a direct integral method from basic calculus. Since dip minus cos are equal to sine, okay, you get the result of this integration by you get minus cos here, and you substitute y0 and L sub y. You know that there's two part, okay, when m is an odd value, okay, since when m is an odd value, okay, you can see that start from you know that the result of this integral is this function minus cos value, okay. When you substitute, okay, when m is even, okay, when m is even, okay, between 2, 4, 5, okay, you always get this when you apply this as 0 and y, it doesn't matter the minus sign mean. The resulting, when you substitute this at L sub y is equal to L sub y will cancel each other, you get minus cos m pi, and when m is even, it's always minus cos of 2 pi is always equal to cos 0, okay. Again and again, you're gonna end up having the same value when you multiply this as L sub y and 0, okay. And with this minus sign, okay, the term will cancel each other, okay. Therefore, when m is even, okay, this integral results 0. When m is odd, okay, but m is odd, the sign, okay, which means is cos pi, cos uh, 3 pi's, okay, of 5 times pi's, okay, times y divided by r sub y. You would get that when you substitute y equal to L sub y, okay, cancel each other, you're going to be cos pi, cos minus pi. When you multiply, evaluate that y is equal to 0, which is equal to 1, but this is a minus, and then the cos pi, cos 3 times pi or 5 times pi is always minus 1. Therefore, minus and minus become plus 1. Okay, therefore, these two terms is just add up to each other. Okay, so when they add up to each other, okay, they get, instead of they cancel each other like when m is even, okay, it becomes 2 times L sub y divided by m pi, because this is a result that you get 1 plus 1, okay, the other get 1 minus 1. Okay, just look at this. This is not a difficult way to figure this out. Okay, so okay, this is L sub y, this one, okay, when m is odd, and this is when n is even. And the result of these two type of right hand side leading to these two conditions. So this C star m L sub y divided by 2 is equal to this value, the 100 times 2 times 200 times L sub y divided by I when m is odd, but this is 0 when m is even. Okay, as you know that when m is even, C star m need to be 0, okay, here, when m is even. But C star m here, L sub y, okay, become 400 divided by m times pi. Okay, since L sub y, when m is become the odd value. Okay. Okay, therefore u of xy, okay, instead of n start from 1 to infinity, n can start from, with a non-zero constant, n have to be only the odd value, the 1, 5, 3, 5, 7, 9, and so on. Okay, the constant value become 400 divided by n times pi. Why? Because here L times Y, they cancel each other. Okay, when you move 2 over here, you get 4 times 4, 100, 400 divided by m times pi. Okay, therefore, when you substitute here, you change m to n. Okay, here you get 400. And this is the resulting of the general equation, the non-trivial general equation for this example. Okay, based on this boundary condition. Okay, and this is the illustration. Okay, and you can apply this type of technique to solve a certain type problem. Okay, so we leave this to homework assignment for you. Okay, if we consider the two-dimensional Laplace equation with x, and this one has a finite value 20, 0 to 20, and y start from 0 to 30 with boundary condition. Suppose that we have all constant here. Okay, 100, 50, 80, 150, and you know that x is not reaching the boundary infinity, all finite boundary, but you just have a non-zero constant for each boundary. Okay, when we want you to derive u of xy when x and y is between in that range, excluding the boundary lower limit and upper limit of both domain. Okay, and then the same way is that we start if we assign for the numerical value, the two-dimensional heat equation. Okay, let me recall back to you. Okay, that we have derived this condition. Okay, for the two-dimensional. Okay, this one. Okay, and then this one is for the heat equation, and you know that the constant value, we show you that they have some derivation in the form of double Fourier series down here. Okay, if you might recall from the last clip. Okay, and we assign this, okay, for this again. Okay, that suppose that u of xy, the boundary condition become function. Okay, and have some constant value and function all together. Okay, we want you to derive u of xy as time t. Okay, let's go and try to find out how you're gonna solve this type of problem. Okay, and we already illustrate an example for you. Okay, now, okay, in the next topic, okay, we'll extend it, okay, the knowledge that we study from the two dimension to what we call the three-dimensional Laplace equation, which we add one more domain we call the C domain, okay, X, Y, and C domain, okay. Just like what we did on the heat equation, we start from one-dimensional and then we go to two-dimensional. And certainly, when you understand the two-dimensional, okay, and you can extend it to three-dimensional. But the Laplace equation, we cannot start from one-dimensional. Okay, we start from two-dimensional. Okay, so now we're going to extend to the three-dimensional. Actually, Laplace equation, you can also work on the one-dimensional also. Okay, but since we familiar with both one and two-dimensional, the Laplace equation we will extend the basic analysis or the Fourier method that we've been applying to illustrate this example for you. Okay, so this is the extended three-dimensional Laplace equation. We had two dimension, we add one more dimension here. And you can go for fourth dimension, three-dimensional, fourth, or in the n-dimensional, okay. But in terms of application, it's more appropriate to only look at the three-dimensional in the real world illustration, okay. So in general now, okay, you should be familiar with the analysis that u of x, y, z is a product of the three separated domain function, okay, for each domain function, capital X, capital Y, and capital C corresponding to each domain, X, Y, and Z. Okay, and it's not, and to satisfy, when you put this substitute, this representation and apply to the original equation, you get this relationship. Okay, the first term you get the second order for the X function, okay, when Y and C is constant. The second term you get second order for the Y function, X and C is constant. The third term is that you get the second order function for the C function, and X and Y, capital X, capital Y is a constant. Okay, and if you apply this, okay, you divide it, okay, by u of x, y, z here, let's say here. If you use u of x, y, z, divide it on both sides of right hand side. On the right hand side, no use. This is it's a ratio that 0 divided by something is always 0. But the left hand side here, okay, the first term become here. Since y and z cancel each other, so the division is only the x function here. The second term also you get here. The third term you get this because x and y you can cancel each other. Just the we could become this is the result for the simplification of this Laplace equation, okay, based on this substitution. And we're going to call the first term here as a capital A, capital B, and capital C. Okay, and you get this simplification that capital A plus capital B, capital C have to be equal to 0. Okay, and we're going to apply a similar technique that we use in the two-dimensional case. You remember the case of two-dimensional case? Down here, okay. We just assume these two equal and equal to k squared, okay. And the same here, okay. But we're going to say that suppose A is equal to constant we call minus k squared. Why you want to say that, okay, this become y sometime plus, sometime minus. Actually, you can use plus or minus as long as you want. It just it's gonna go let's just say in the reverse way. Okay, so it doesn't matter. It's just the way you assume the value in the first place. Okay, suppose a is a negative value. This is minus k squared. Okay, in this form is a negative value, and b is minus l squared less than 0. Okay, actually this technique you should be familiar when you analyze the two-dimensional heat equation from the last clip. Okay, so therefore if a and b is equal to this value or negative value, c must be a positive value, and c must be equal to k squared plus l squared, so that this equation will be satisfied. Okay, again, if you trying to say, suppose a become positive value and b become positive value, therefore c become the negative value. The same. Okay, you can use that as assumption also. Okay, so every which way gonna end up with the similar results. Okay, but just the reverse, just like sometimes x function become y function, x and y have some different form. Okay, but the general form, okay, is the same. Okay, so based on this substitution, you get these three corresponding differential equation, ordinary differential equation. Okay, by using this. Okay, so this is what very similar to what we did with the two-dimensional heat equation. But actually, when you study two-dimensional heat equation, there's three domain, because we have t domain adding one domain, but the t domain is missing here in the Laplace equation because of the steady state condition, as we explained before. Okay, and again, when you get this and you get k square is a positive value, okay, you end up, okay, down here, okay, you get this general form. Since the real part is equal to 0, you get complex conjugate root here. Okay, for the auxiliary equation, this is general form of x. And L square, same. But c, since this is a positive value, okay, so you get a real root here. Okay, you get plus or minus square. Okay, so this is the general formula. As I told you, that you get different type of things. Okay, if you just say that, okay, I'm gonna say if a is a positive value and b is another positive value, c is positive value, therefore b have to be the negative value. Okay, that gonna end up having a different type of form, but the results, okay, in the general form will look similar to each other. But just that instead of x gonna look like this, x become look like c, y become the same y, and then sometimes y become look like c function. And you can try, and then, okay, sorry, we're gonna go here. We're gonna try and take a look at the uh, different type of form. Okay, when you make this different assumption of a, b, and c. Okay. So with this assumption of capital A, capital B, capital C, resulting to this general function of u of x, y, z. Okay, u function corresponding to three domain x, y, and z. Okay, so there are now the six constants: c sub 1, c sub 2, c sub 3, c sub 4, c sub 5, and c sub 6. Okay, and again, this constant value rely on what you define your boundary condition. And with this boundary condition, we're going to extend that. Okay, L sub x and L sub y, and the one L of c is the upper limit of three domain, okay, uh, respectively, and all domains start from the lower limit of 0. And in this case, we're going to assume that all boundary condition is equal to 0, except at here. Okay, at the upper limit of c, okay, of c function for all x, y, okay, the u of xy at L sub c is equal to a constant value we call v sub 0. Okay, v sub 0. So this is not the numerical value. It's a general function. That suppose that one size of the boundary condition has a constant value, and we can continue to analyze this problem in a similar way that we explain in the two-dimensional case. Is that each boundary condition lead you to eliminate some of the constant value and simplify this function, okay, in the more concise form. Okay, we can see that, okay, for this one, okay, if you start at 0, okay, at x is 0 for all y and c, okay, so this one you can see that with the separable function, okay, of y and c equal to 0, therefore x0 must be equal to 0. Why? Because you can see that for all y and c, okay, you cannot control 0 here in general, but you can, when x is equal to 0, you can know sine 0 is 0, therefore the only term here is cos 0 is equal to 1, the constant 1 here multiplied. Therefore the only way that this condition, okay, will be satisfied for y and c, okay, you need to make sure that c sub 1 is equal to 0 here, which is here. If c sub 1 is always 0, since this term, okay, it's all guaranteed for all y and c that this condition satisfied. Also, okay, at u of x at y0 for all x and c of 0, okay, this is this second term, okay, of y0. So when y is 0, the same as when x is 0, okay, c sub 3 need to be equal to 0 because this term is always 0 vanish. Okay, but to make it control for all y and c within the boundary condition, within the range of the domain, okay, of both y and c, of x and c, okay, you make to make sure that c sub 3 is 0. And again, we started when c is equal to 0, okay, u of xy is 0, you have to be equal to 0. This one, you look at this term, okay, and you know that when c is equal to 0, okay, when z is 0, okay, you get this constant term c sub 5 plus c sub 6 multiplied to these two functions. Therefore, okay, it's only guaranteed that c sub 5 and c plus c sub 6 must be equal to 0. Or in other words, okay, c sub 5 have to be equal to minus c sub 6. So these three conditions, okay, that we use, okay, lead to the elimination of several constraints and a combination of some term. Okay, like the first, okay, x function, this is the only remaining constant is c sub 2, that related to c sub 2. And the second term is only this, okay, c sub, okay, 2 sine of kx and c sub 4 times sine of L times y, okay, times L times y. And you know that y, k, and y, because this is in general form, and k and L is coming from this assumption, okay? And in this one, okay, when you have c sub 5 here, okay, and c sub 5 is equal to minus c sub 6, okay, when you apply to this last term, okay, you can put c sub 5 constant, okay, multiply by this one. And this one is instead of plus, it become minus because c sub 5 equal to minus of c sub 6. Okay, so this is e to the minus a square root of k squared plus l squared, okay, times c. And the second term minus e to the minus of square root k squared plus l squared, okay, all together minus c, times c, okay. And this one, you can simplify this as what we call the sine of x, okay, sine h of x, okay. Okay, this is a well-known definition, a mathematical definition, okay, sine h of x, okay. Okay, how do we call this? Okay, you might take a look, ask for the, okay, sorry, Wikipedia, okay. What is sine here? Okay, this has the definition of here. Okay, you can find here. It's a hyperbolic function here. Okay, okay, hyperbolic trigonometry. Okay, and if you want to spell it, okay, you can ask the Google to help you also. Okay, well, I'm not gonna go to that. Okay, you find it yourself down here. But I'm gonna call it sine h. Okay, or back down here. Okay, it's a hyperbolic function. Okay, so this is a form of this sine h is for hyperbolic. Okay, the hyperbolic function down here. So we just put this substitution down here. Okay, and since okay these two terms okay, okay are so familiar, this one minus. You need to divide it by 2, but this one is only they're not divided by 2. Therefore, the resulting of this substitution, this e to the x minus e to the minus x need to be equal to 2 times hyperbolic function of sine x. Okay, this one get the results here. 2 c sub 5 hyperbolic function of sine of square root k squared plus l squared altogether times x. Okay. And the next step is that we can use the remaining two boundary condition here. The the zero boundary condition here. This one evaluated at the upper limit, okay, of both domain x and y, and L of x and L of y. This very similar to the two-dimensional case. You get with this simplification term, okay, when you substitute x at the upper limit, okay, you know that okay, that you can't control the zero value for all y and c based on these two functions. Therefore, the only way to control zero is to make this term zero. And to make this term zero, okay, you can find the k value. K need to be equal to n times pi divided by L times x for the positive value here, always positive, okay? Uh, and when n start from 1 to infinity, therefore you get here, okay? This is a condition of k. And the second one is all else of y, okay? Therefore you can here sine L, okay, and this is L sub y. L, this is a different L, okay, this is L sub y, the upper limit of y. This is the L, the constant that we define here, okay, that the b value is equal to minus L squared. Okay, so with these two conditions, you can get the condition of k and L, and then therefore you get k squared plus L squared, okay, by putting in this substitution, okay, and you have a common value of pi, okay, and since this is square, okay, pi square become a common multiplication, put it in here, and this is also guarantee always a positive value, so we assume this value equal to lambda square and rely on two parameters we call n and m. Okay, therefore the parametric function of the u of x, y, z rely on two more parameter, the one more parameter instead of when you consider the two-dimensional case of Laplace equation, which rely on only the n. Okay, this one n and m. Okay, u of n and m. Okay, of x, y, z. Okay, and you can know that c sub 2 here. Okay, c sub 2 rely on the n. Okay, rely on, since this is a multiplication of this term of k. This and 4 c sub 4 rely on m, because this one is an L function here, the time size of L times y. Okay, and but the fifth one here, c sub 5 here, all rely on n and m because they have this one, the c sub 5 times the hyperbolic function that rely on both k and L. And we already simplify k square root k square plus L square c here, okay, by using k square by L square, substitute by lambda square of nm, okay, sub n and n. Okay, so this one become this function, and this one become c sub 5. Okay, we're gonna call the new c sub 5. Okay, have to be c star. Actually, they have a constant c, but constant time constant is always remain the constant. Okay, this one should be c star or sub 5 nm. And you can see that c sub 2 and c sub 4 and c sub 5 can simplify by multiply to each other, and you get the new this one we call C star, okay, of n of n, and this is the x function, the y function, and this is a c function that rely on n and m. And with all combination superposition principle, you can combine all these functions as a general form of u of x, y, z. Okay, so the remaining part here is that you need to find c star of n m. Okay, and c star of n is all multiplication of all constant, and lambda of n m is a k and a k square plus l square. Okay, time okay okay this one lambda k square plus l square down here. Okay, to find c stars of sub nm, okay, we need to use the last boundary condition that we said, where at the upper limit of L sub c we get a constant non-zero constant value v sub 0. Okay, and so therefore, okay, if you substitute L sub c to the c value on the left hand side, so this one is lambda nm L sub c. Okay, the left hand side become v0 for always, and we're gonna try to use a similar analysis that, okay, over here, okay, but we're gonna multiply on both sides, okay, with sine. This one you have sine, you get n inside there, we got n pi, and for m we have m pi. Okay, we multiply the similar form of sine. They rely on n and m on both sides. Okay, this is on the left hand side. On the right hand side, okay, instead of v0, you have these two terms. Okay, and find the integral on both sides. Okay, start from 0 to L sub x and 0 to L y. They rely on this and each domain. And you can separate this double integral on both sides because each function is separable to each other in the multiplication form. Okay, so and this term is become a constant because you just move it outside here. Okay, the c function here, the hyperbolic function, and this is a constant here. So now you get another integral of sine integral sine, and the left hand side integral of sine. So isn't that familiar? Yes, I think that is the same technique that we've been using all along from one-dimensional case to two-dimensional case. Remember that? In two-dimensional, we use this, okay, to simplify to get this result. Okay, even for heat equation also. Okay, we're using this type of equation to simplify the same as we apply, okay, both on heat equation and on two-dimensional Laplace equation. It's not the left-hand side will become, okay, it start from c star from n pi and m pi. There's only one term here. Okay, even though summation, because when n is equal to n pi and when m is equal to m pi, it's the only case that you get the non-zero value. For when n is not equal to n pi and m is not equal to m pi, all terms are zero and vanish. Okay, for the left hand side also, okay, it's gonna happen when only when n pi and m pi become odd value, not an even value. Because remember that for two dimension, okay, we get this condition, okay, when have a non-zero line hand side only when m is odd and when m is even. I think it's happens similarly here. Okay, we're not gonna show you, but it just continue the same spirit. Okay, when either when n pi or m pi are even, it's all zero. Okay, or not and, okay, not both, but either one of them. If one of them is even value, even the other one is odd, is always zero because it's in the multiplication form. But when both of them are odd, okay, you get this. Okay, you get 4, okay, times L sub x times L sub y n divided by n pi m n pi times n pi times pi square. Okay, this should have a close bracket down here. Okay, so now you can see that c star n pi m pi here. Okay, you can now simplify it. Okay, here. Okay, c star n m. Okay, with 0 when either n or m are even. Okay, Okay, when both of them are here. Okay, this is a y16. Okay, you can do it here because this is the left hand side. Okay, here. Okay, this is a constant Lx sum as y dy, and this is the right hand side. Okay, this is divided by 4. When you move to the right hand side, this becomes 16, and Lx and L sum y cancel each other. Okay, so it becomes 16 divided by this division times this hyperbolic function, and that's resulting here. And we just put it here in the general form. And since this is a constant, you move, it's not rely on both n and m. Okay, you move it to out, and then you get summation. When n and m is both odd value, you get this general function. Okay, this c function still remain. Okay, but the sign, okay, this is in general form. This is the division that resulting from this constant. That, and you have to put it in the summation because it's rely on the n and m. Okay, so that's the conclusion of the results. Okay, from based on this derivation. And I also leave you with this problem. Okay, that suppose we want you to solve for u of x, y, z in case of 3D Laplace equation based on this foreign boundary value condition. It's all non-zero here. Okay, it's all non-zero. It's have a three of the three sides of boundary condition in 3 dimension is a constant value v sub 1, v sub 2, v sub 3, and then for the at the upper limit become a function that rely on the remaining two domain. Okay, and you go and try to figure out by based on the knowledge that you learn from this clip. Okay, and then we will have some tutoring session to review how to solve this type of problem again. Okay, that wraps up about our 2 or 3 dimensional Laplace equation here. Okay, we still have one more topic left about partial differential equation, which is a classical what we call the 1 2 dimensional wave equation. Okay, until then, I'm gonna close down this clip. This lecture for the lecture for this clip now. Okay, and we see you in the next clip.